Okay, in this video, I'm going to begin to introduce the final project, which will be the last major assignment in this class. The final project is going to be a team assignment. What I'd like to do today is kind of walk you through at least the first half of the assignment and give you some pointers on what you might be able to accomplish as you return from fall break on the two in-class work sessions on Tuesday and Thursday, again, following fall break. Okay, so the project is set up in the following way. There's two major sort of like mini components to the project. One is focused on the input-output model that we've been using for LCA. We're going to take a pivot in the project and actually use it instead for understanding interdependencies, and in particular what happens when you damage one piece of infrastructure, how that damage propagates through the overall infrastructure systems and ends up damaging things beyond what you directly impact. The second part of the assignment is going to look at how people supply electricity and how you can use tools from decision sciences, in particular optimization, to make intelligent choices about how you produce electricity to meet a variety of objectives, like to make power very cheaply, to make power with relatively low risk, or to make power with relatively low environmental footprint. And you can imagine wanting to make power that kind of trades off a combination of those criteria. And in the project, you'll have an opportunity to explore that. The second part, this part on the power generation, I'm not going to say too much more about because, one, we haven't covered any topics in optimization. We will do that following our return after fall break. And two, you'll need to know some details about how to actually implement optimization problems so that you can solve those decision-making problems. So kind of the goal I'd like for you to do as an outcome of this video would be, one, get a pretty good understanding of what the first part of the project is doing. In class on Tuesday and Thursday during those work sessions, please work with your teams. They will be the same teams as last time. I didn't hear any concerns about the teams, so those can be fixed as they were for the previous assignments. And then really do your best to make progress on the first set of questions, because I'm going to assume that that is probably the easier part of the project, and I'd like to make sure that we've got a good jump start on that. Okay, so I'm going to maybe spend a few minutes walking through kind of the overarching objectives of the assignment and what you can expect, and then we'll dive into some of the input-output modeling. Okay, so the main key piece to take away at the very beginning, it's a final project. It's due on Friday the 13th, 11:59 p.m. That is very precise. If it comes in later than that, we won't be able to get it graded and turned around in time for the grades to be posted. So that's going to be a hard deadline. We won't have any extensions there. What we do have is flexibility on just about everything else. So one thing you'll see right away, this document I'm going to put a version number on, because as we work through the project, you may raise questions in class that are actually really good questions that may break part of the assignment or may cause us to want to explore another area in more detail than others. So think of the project description as more of a roadmap of things to try and to explore. And depending on kind of the interaction we have in class and where things get headed, we might need to revise things. We have done our best to make sure that there's no sort of mathematical problems in the project where if you plug something in, you won't get a solution, or a matrix isn't invertible, or things like that. So we have checked pretty carefully to avoid those types of errors. But inevitably, if you're having trouble with your code, either your code is broken or something is wrong in the mathematics, we'd like to get that fixed. And we'll be there to help support your team as you explore this. Okay, so more detail, it is a group project. And so we'll be using the same type of rules that we've had in the past for the group assignments. I am expecting that you are going to talk to other teams to get intuition on some of the problems. But I do need everybody to each team to submit their own work, and in particular submit their own code. If you need input from another team to help you debug, that's certainly fine to get input on, but I don't want to see things like code being exchanged between groups. You should be able to collaborate on, for example, a whiteboard without getting into like just brute force copy pasting of code, things like this. So when in doubt, raise the issue, and we'll be happy to walk you through to make sure that everybody's working on a fair playing field. The next part in here tells you that parts 1 and part 2 can be explored in parallel. That's true to some extent. I think for the purpose of how we're going to organize things, I'd like you to read through the entire assignment, including part 2. But I don't really think that you need to make too much progress on actually doing any work for part 2, at least until we're back all in the same place. So put most of your energy on doing work on part 1, reading part 2. Okay. The final part here is that, by the way, there's quite a bit of work that has gone into putting this project together, based on relatively recent references that kind of explain the inspiration behind what we're doing. So, for example, if you click on the reference list and scroll down here you will see reference 1 is actually a study that was done by the California Energy Commission so that they could figure out how to meet a stated goal to hit 33% of the state of California's energy production via renewable resources by 2020. That's actually a really hard design challenge, and you'd like to do it in a way that is low cost, that has low risk of high cost, things like that. And so we took this report and kind of simplified some of the problems and used that as the basis for the second part of this project assignment. So definitely a good reference to download and have a look at to maybe get a little bit more context for what's going on there. The bottom 3 references here, you will see, the bottom 2 references here are more closely related on the risk side, where we look at using EIO models to do risk assessment. And you'll see reference 4 is actually called the Leontief-based model of risk in complex interconnected infrastructures. You know where this came from. Leontief was the economist that won the Nobel Prize for the EIO models, which were later repurposed to make EIO LCA tools. The model is developed in reference 4 that we'll be using as part of this project. And some of the data that we've used is coming from this third reference. So in particular, this third reference, I might suggest if you're looking for more reading and more detail about how the math comes together and what the terms mean, there's a lot of very detailed descriptions that come out of this reference that you might find quite helpful as you try to answer some of the questions that we've lined up for you. Okay, so all the way back to the top, just scrolling back through here, yes, you can see it's a pretty healthy and long document here. What do you actually have to deliver? Well, on this project, I'm expecting a final report for each group project. I need it typed up in something, Word, LaTeX, whatever your favorite type editor is, but you will need to produce. In fact, even a really well described Jupyter notebook could get you most of the way through. But I will need some kind of professional looking final report. We also will need to have a copy of any Python code that you use to solve any of the problems. Again, that's most likely going to be in the form of a Jupyter notebook, but I don't know, there may be something else you come up with creatively, especially in the optimization space. There are some optimization tools that are not directly part of Python. I'm not expecting you to use. If somebody wants to explore some of those tools, I'll be happy to show you what they look like. I would need the code that comes out of those tools to verify that your optimization tools are working. I will ask for 2 really intermediate project presentations. The first will be on in class on Thursday, Thursday, November 4th, and then a second one on Thursday, December 6th. The progress report, I'm not really too concerned about you giving me a detailed description of comprehensively your solution to all of the problems. What I'd really like to hear from you are what parts of the problem you think you've solved correctly, and I can give you feedback as to whether or not I believe you've solved them correctly or not. And similarly, which parts of the project you are struggling on. If every team is struggling on the same types of problems, through these presentations, my hope is that we can maybe get a little bit more detailed work on the board or inside some of your code to help get each team through the challenges that are being encountered. And so really the first one is more just to help me make sure that your team has done enough progress to have a fighting shot at finishing the project on time. The second one, I'm expecting you've done a lot more work. By the Thursday, December 6th, by the way, is the last in-class activity that we have together. My guess is that when you're presenting your most prized result, I may have a question or spot something that concerns me in terms of one of the plots. I'd much rather you know that on Thursday, December 6th, that there might be a bug in your code that you have an opportunity to fix before you actually submit the final report, which is due a little more than a week later. So there's a gap in there between the last time you give sort of informal output in terms of what you've been able to do, what you think is right, why you think it's right, and the time where I'm actually going to be grading what you've done. Right. So view these as sort of check-in points. They're opportunities for you to collect, to present information to me, and also to get feedback from me about whether or not your solutions look good or not. Final report again due on Friday, December 13th. I'll take it up to the last minute of that day so that we can get things returned on time and get the grades posted. Kind of going along with that, maybe just a word of caution. There are a number of questions in this project, some of which are very, let's say, meant to be easier, and others that are meant to be extremely challenging. And I'm not expecting I'm not expecting anyone to submit a perfect report in terms of complete, perfected solutions to all of the problems. But I would like you to hit a minimum threshold, and that will be kind of iterated through as we collectively talk about these through these presentations. But I would like you to make good progress, and don't worry too much about if you're not able to answer every single question on the project. That's not actually going to have a dramatic impact in terms of your final grade, right? As long as your teams are working together and you're tackling interesting questions, you may spend significantly more time on a question that I think has a simple answer. But if it's interesting to you and you spend more time and explain to me why it's interesting, obviously you're going to have to put less effort on other parts of the project. So we'll keep that in mind as we go through this. It's meant to challenge you, but not break you, and we'll make sure that the grades and sort of the expectations in terms of how complete the projects are reflect the fact that I know you individually, everyone is putting in a lot of effort in this class. As we've done in the other group assignment, I will need a statement of contributions that really just outlines kind of what each team member is doing and what the percentage contribution to the overall project each person contributed. That just makes it easy for the dialogue to occur before the final project is due. If a team member is not necessarily contributing as much as they should because of schedules or other things, they might have an opportunity to make up for some of that effort in later stages of the project, so that we can know that everybody's contributing in a way that is fair to all team members. The usual piece about the academic code of conduct is here. Anytime there's any questions on that stuff, again, raise it. It's tricky in the software space to do what is ethical. Obviously, my main goal is making sure that everybody is learning in the class. And so if that learning is occurring through exchange with other teams and other dialogue, that's actually a good thing. We just want to make sure that it's done in a productive way and not in a way that isn't maybe slanting the field in an unfair way, so that some teams are getting answers to solutions that they really don't understand or haven't carefully thought through. Okay, so that's kind of the boilerplate at the high level. Any comments or questions on that, we can either take via email, office hours, or in class. Just raise those for me, and we'll be happy to spend more time on them. Let's dive into now the infrastructure interdependency analysis. Okay, and so that input-output interdependency analysis really stems again from that core mathematics of input-output modeling, whether it's used for studying the economy, studying infrastructure, or studying the environment, is really up to the interpreter of the mathematics in terms of what data you use to plug in for the matrix A. So the story in a nutshell, you will see by the time we're through here, a matrix equation or a system of equations where you have something along the lines of x is equal to ax plus f. That's the same whether you're doing the economic input-output model or whether you're doing an interdependency model. F is going to be some kind of final demand or some kind of external something that you want to understand what it does to the rest of the economy. There, x is a total amount of economic activity. in each of the different sectors, or in the case of the interdependency model I'll explain, X will turn out to be something like the total amount of damage done to each part of the infrastructure. So where does this stuff come from? Well, it turns out that critical infrastructure systems, the ones that we started off at the very beginning of the class saying that infrastructure that people depend on kind of gets elevated to this notion of critical, whether it's a critical bridge going across a river or, I guess you could call the power system critical infrastructure. The internet is now becoming a piece of critical infrastructure. You want to understand sort of how that infrastructure is linked to other infrastructure systems. It's not that we have a bunch of independent infrastructure systems where damage to one piece of infrastructure does not cascade into other parts of the infrastructure. Now, because the systems are coupled spatially, physically, and increasingly through cyber technologies, it's really hard to understand what infrastructure you need to protect because everything else depends on it. And kind of a weird way that you could think about it is it may be possible to have a non-critical piece of infrastructure in terms of if it directly disappears, nobody's going to be disappointed about the lack of that specific piece of infrastructure in the short term. But the fact that other infrastructure systems depend on that infrastructure and those other infrastructure systems are critically important, it still may be worth protecting. And weird things that have happened in the past when in New York City, when Hurricane Sandy hit New York City, some of the subway tunnels flooded. Well, the subway is a piece of critical transportation infrastructure, but it's not viewed as something, well, like if the tunnel is flooded, well, we can obviously still put people on buses. It's not a great solution, but it can get around the fact that there's water in the tunnel. What became a problem is that there were electricity and parts of the power system that were buried alongside that tunnel. And when the tunnel flooded, it wasn't just that you couldn't run the subway through there, it was that you could not run power through that tunnel until the tunnel was emptied from water. Well, all of a sudden now you don't have electricity in a good part of the city. That is now making that tube a piece of critical infrastructure, even though we don't necessarily put as high a priority on the mobility side as we would on the power side. Not having power means you might not have electricity in a hospital, you might not be able to keep food cold or keep buildings warm and so on. So totally different set of conditions rather than just having to take a longer pathway to work. Right? And so these interdependencies, how one piece of infrastructure depends on another, and how that same piece of infrastructure may depend on the first piece, this coupling of infrastructure systems, is a really nasty business that the National Science Foundation, the Department of Homeland Security, Department of Energy, a number of other agencies are pouring a tremendous amount of money into so that they can better understand how to spend scarce resources to maximally protect infrastructure systems that may possibly cascade. Okay, so with that kind of as the overarching setting, an interesting piece comes in with these so-called direct dependency. Direct dependencies are quote, the easy types of dependencies to both identify and analyze. So a direct dependency would be that, like, obviously, like our campus depends on power. If the power goes out, we can't have class, right? It's pretty difficult to do with that. That's pretty easy to see for many direct dependencies. But even the, quote, easy problems, the direct dependencies, can be subtle and can be hard to identify. And there was a very famous example that's used pretty frequently to motivate these types of applications that happened in the late 1990s when a satellite system started to go offline. And obviously the satellite system was used for pagers. I'm not even sure if I want to try to explain what a pager is, but maybe Google what a pager is to figure out how people communicated before cell phones existed. But pagers are still used today by doctors and by a lot of people in the tech community. It basically is a pretty reliable way to send somebody a note to call you back, and the only thing they get is information about the fact that a specific phone number called them, and then you go to your nearest payphone or grab your cell phone or whatever and call people back. So pagers were used pretty regularly. Well, okay, so fine. The satellite system goes out and the pagers go offline. 40 million pagers stopped working when the satellite went out. Well, that was pretty easy to directly see. because the pagers were using the satellite system. What was more subtle is that, hey, a bunch of United Airlines flights went offline because they didn't have high altitude weather data that also came from the satellite system. Even harder to see was the fact that a bunch of gas stations were going to go offline because the links from the credit card swiper at the gas station also depended on that satellite system. So here you are trying to fill up gas, and because a satellite that you've never seen, never been able to touch, stopped working, you can't put gas in your car because you can't swipe your credit card and pay for it. Well, that's actually relatively hard to see. And if you start thinking about who was using gas and who's not able to do refueling and what that impacts in terms of the economy, you can start to see pretty quickly how even the direct dependencies, when you go into the second, third, fourth, fifth order effects, get pretty tricky. What gets even nastier is when you have sort of loops between the infrastructure systems. So you might have a power system which depends on delivery of fuels. If you've got a power system that's burning gasoline or diesel or something like that, and obviously the diesel is delivered through the transportation network, but if the electricity goes out and the gas stations are not able to sell the fuel to transport the fuel, you've got this weird double coupling where you can't get power because you don't have gas, and you can't get gas because you don't have power. Well, anytime you have those loops, things get even nastier in terms of trying to figure out the total amount of impact that you can have with a system. This was no different in the process-based LCA. We saw those interdependencies when we saw things, when we added the extra link and said, hey, electricity production depends on fuel and fuel depends on electricity. All of a sudden, we weren't able to mathematically analyze it just by looking at it. We had to actually use some linear algebra to find sort of the total impact. Well, the same is true when you think about infrastructure interdependencies. When infrastructure X depends on Y and Y depends on X, it's really hard to see if I damage X, how much total impact will occur to X and how much will occur to Y. Well, these interoperability or inoperability input-output models actually give a mathematical framework to start to do this analysis. It comes with all of the same limitations that the EIO models come from, right? All the linearity assumptions, all sort of the aggregation assumptions, slightly different meaning of what those assumptions do, but they're all still baked in. It is a linear model. It is a static model. It doesn't treat infrastructure systems as a particular gas station or a particular power plant. It looks at them all together, right? So that's both a pro and a con. It makes it really simple to apply, easy to analyze, but obviously not as high resolution as if you go in and model in detail every piece of infrastructure you've got and how they couple together. What does the input-output model look like? Well, the storyline, here it says, right, the math is identical to the EIO framework we already know that we applied to LCA. The only thing that's different is how we define the meaning of the variables. So we start off in the usual way. We're going to let X, which is a vector in Rn, denote the vector of degradation of the n elements of infrastructure. So let xi be the ith element in that vector, right? Literally what xi means is the total level of degradation of that infrastructure. So if xi is equal to 0, it means that the infrastructure is completely operational. If instead xi is equal to 1, it means that infrastructure has completely failed, right? So xi equals 0, everybody's got power. Xi equals 1, no one has power. Okay, so xi is the total damage to the, in this case, I equal power infrastructure. Okay, we're going to let fi, rather than being the final economic demand, we're not dealing with the economy anymore. We're going to let fi denote the external shock to a piece of infrastructure. So let I be the power network, and suppose that fi is something like the direct damage as a result of an earthquake to the power network. Obviously, the earthquake causes direct damage to the power network. What's harder to see, and what the model will help us tease out, is the fact that the power network is out means that the fuel network is going to be operating at a degraded state, and the fact that the fuel network is operating at a degraded state may add additional damage to the power network, even in areas that initially had power and were not damaged by the earthquake, say another power plant, might not be able to operate because they can't get the fuel they need to operate long term. So you get a weird dependency where the first thing causes direct damage but may not be complete damage, but the effect of that incomplete damage causes other infrastructure to become damaged, which further adds on to the damage to the power network. Okay, so Fi is this external disturbance. What I want to know is Xi, the total amount of damage to the infrastructure, and not just for infrastructure I, but for all of the I infrastructures. Okay, so what we're going to do is we're going to look at how much of the damage is sustained from this external source. This is the Fi, the external earthquake, let's say, and we're also going to look at all of the intermediate damage caused by other infrastructure not operating completely. So we will let OI be the cumulative damage to infrastructure I caused by all the damage to all the other infrastructures. So let Xi be the degradation of infrastructure I caused by degradation in infrastructure J, and we'll let OI just be, again, like a row sum across all the different infrastructures that are damaged, that when they are damaged are adding damage to infrastructure I, and that will give us OI, the total amount of damage sustained to I from all the other infrastructures J. Okay, this will give rise to an equation that looks awfully similar to one we've seen before. The total damage to infrastructure I will be nothing more than the sum of two parts. The first part due to the damage, well, I guess if we follow the text here, the first part is due to the external disturbance, i.e. the earthquake. That earthquake damages a lot of infrastructure, including the ith infrastructure, but all that other infrastructure that's damaged further damages the power network, for example, and the sum of all of those other infrastructures that are damaged that also have an impact on or further damage infrastructure I will be the cumulative damage caused by all that other infrastructure OI. So total damage is the direct damage caused by the external source plus the internal damage due to all the other infrastructure operating at a degraded state. Okay, so far we haven't done anything too different from what we've seen before, and the process continues. Instead of working with the x's directly, what I need to really know is these coefficients Aij, where Aij is going to be a proportionality constant. It's going to tell us how failures in infrastructure J propagate to infrastructures in I. In other words, if xj is equal to 1, that says the jth infrastructure is completely damaged. What I want to know is how much damage that does to infrastructure I. Well, Aij will tell me how damage in infrastructure J relates to damage in infrastructure I. Okay, and that's no different than what we did in the EIO model. We introduced Aij in the EIO context as just Xij divided by Xj. Well, it's the same equation, just written in a different way here. Okay, and kind of the power of this equation is, again, it's going to tell us how damage in the jth infrastructure creates additional damage in infrastructure I. Okay, so if Aij is 0, that means that no matter how damaged or operational infrastructure J is, it does no additional damage to infrastructure I. That's actually a good thing. It means infrastructure I does not depend directly, that's the key phrase, directly on infrastructure J. It may be hidden behind us that infrastructure J damages infrastructure K, which damages infrastructure I. But if Aij is 0, it means literally J does not directly cause I to be damaged. On the other hand, if Aij is 1, what that says is that if infrastructure J is completely damaged, it means infrastructure I will be completely damaged too. It will propagate completely. All of the damage from J will go through to damage to infrastructure I as well. So you can see Aij is really about the direct influence of damaged infrastructure J to infrastructure I. Well, again, we don't necessarily care about the direct damage. I mean, although that's interesting, The most powerful thing is sort of the total damage that's either caused by direct or indirect effects, right? And that will ultimately get to what we really want to know, which is when there is a damage Fi that we specify, what's the total Xi, the total damage caused by the direct damage plus all the intermediate damage. Okay, so if we have this Xij is equal to Aijxj, the usual substitution trick will apply. We'll take equation 2, we'll plug it into equation 1, and if we expand that out for all of the different infrastructures I, we're going to end up with a system of equations, one for each infrastructure, where the total damage to infrastructure I is the row sum of A times the column vector X. That tells you all the intermediate damage done to that infrastructure, plus Fi, the total external damage done to infrastructure I as a result of an external source. Well, that's true not just for the first infrastructure, the first row in this system of equations, but it's true for the second one, the third one, the fourth one, and so on. So we end up with a matrix equation where X is equal to Ax plus F. How do we use it? A must be given to us. That tells us the model of how damage from one infrastructure propagates to the other. We learn that from data. We specify later then a final, like an external shock to the system. We take out the power network. We let an earthquake destroy 25% of the road network. And what we want to know is, if you destroy 25% of the road network, what's the total damage done to the road network? It may be more than 25% because of indirect dependencies, where I damaged the power network. The fact that the road network was degraded meant the power network was degraded, which further degraded the road network. I'd like to know the final X, which is the total damage done to all of the infrastructure as a result of a direct impact to one or several infrastructures, and their sort of intermediate effects. The fact that other infrastructure is damaged causes further damage to the total infrastructure. So this will be the system of equations we have. We, as the user of the model, will specify F. We will have A given to us, and we will be solving this system of equations for n unknowns, n equations for xi, all the n xi's. Okay, so this is just really a new stylized version of what we've already seen. Part of the reason I'm doing this is because I really didn't want to give everybody a 425 dimensional system to do for the EIO model. So instead, we're going to look at a much more stylized infrastructure example where there's only 11 types of infrastructure. We'll look at the air transportation network, electricity, wired and wireless communication, water, finance network, fuel, natural gas, ports, and satellite communications. Where did the example come from? Well, this reference right here, which you can find, again, at the very back of this document. And I'm giving you the matrix A for these 11 infrastructure systems. This infrastructure system A actually came from not just this reference, but these folks actually talked to a bunch of experts and said, hey, if we turned off infrastructure 2 for 6 to 12 hours, how much would that reduce your operations in sector 1? And they came up with an answer of about 13%. They asked the same question to sector 3. They said, hey, if we took offline our sector, how much would it impact your sector? Oh, it's about 10%. So they got these coefficients by actual surveying these operators of different infrastructure systems. And you get interesting things, right? Like, what is sector 11? Well, sector 11 is a satellite communication and navigation sector. And they have things like, well, okay, if you take off sector 2 and you want to know how much damage that will do to the satellite communication and navigation sector, the answer is nothing. Like, sector 2, electricity is not used in the satellite communication system. The satellites are in space and they're powered by solar panels. Electricity on the ground does not impact them. Whether you have electricity on the ground or not, this says that you will not degrade the operation of the satellite system because of lack of power on the ground. So you can see right away the fact that there's a bunch of zeros here are telling you something about how damage on other infrastructure propagates to the I equal to 11 infrastructure here on satellite communication navigation. Basically, it doesn't, right? On the other hand, and I'm just kind of scanning the numbers here, you may find, it looks like this is a relatively large number. Sector 1 depends actually quite heavily on damage to Sector 2. Right? If the electricity network goes out, a lot of that damage will propagate to Sector 1. Similarly, we have a pretty high dependency of Sector 2 on Sector 9. If Sector 9 goes out, that is the natural gas sector, that's going to have a pretty big impact on Sector 2, the electricity sector. Why? Because a lot of the electricity is actually generated from natural gas. So you can see how the data here actually comes about and what it actually means. There is a requirement. It stems from a mathematical requirement that all the diagonal entries in this A matrix are 0. In the IO world for the infrastructure systems, what that means is that the fact that Sector 1 is damaged does not cause additional damage to Sector 1. You can argue whether direct damage to Sector 1. You can argue whether that's a good or bad assumption. I'm telling you for a fact it comes out of a mathematical requirement that researchers have kind of reasoned that might not be a terrible physical assumption either, but it has to do with wanting to make sure that you can invert these matrices. That's kind of why that requirement starts to pop up. It's not guaranteed, by the way, that I'm simplifying a lot of mathematical proofs here, so don't take it as a rule that just because you put zeros on the diagonal, the matrix I minus A is going to be invertible. But for this specific system, they need to have that thing zeroed out in order for it to be a mathematically sensible model. And it happens that it's not a totally crazy assumption in doing so. Then the next couple things that pop up, if you look in reference 3, this is described in more detail. And if you look in the lecture slides on the last video I went through on the EIO models, I did an explanation of what row sums and column sums of S mean, not of A. Well, row and column sums of the A matrix also mean something. And the key word here is going to mean something in terms of direct. I'll let you think a little bit about what that could be, and maybe reading reference 3 might give you some further inspiration. But basically, the question is, what does a row of A mean if you sum it? What does a column of A mean if you sum it? And I'm telling you that one of these things is called a dependency index, and the other one is called an influence index. And those names were not chosen arbitrarily. They stem from what these things mean. Just a little bit of explanation. This thing doesn't exactly look like a row summation. Hey, define kappa sub I equal to 1 over n minus 1, the sum for all the j's not equal to I, aij. That does not look like a row summation, but I'm telling you that it is. Another way of saying this is kappa I is equal to the sum of aij across the j's. The only extra sort of notation decoration that's on here, because these diagonal entries are all 0, we don't want to count the one, the A11 or the A22 or the A33 when we're doing those row sums because they're 0. And since instead of dividing by n, since we didn't count that diagonal entry which is 0, then we were going to do 1 over n minus 1. So as long as you're consistent, if you sum this thing, you sum over all the j's, including the diagonal entry, and then you divide by n, you'll get a slightly different answer. It won't be consistent with how other people compute things, but the meaning will be similar, right? So this one just explicitly accounts for the fact that the diagonal entry is 0. So instead of dividing by n and including the diagonal entry, we drop the diagonal entry and instead divide by n minus 1. Okay, so far we have the data for the matrix A. There are some things we can calculate on that matrix A if we want to. And what we're going to do is get into to some questions. These questions that we're going to outline, I think between in-class activities on Tuesday and Thursday with your team, and maybe a little bit out of class time, your team should be able to either make a really, really good start at answering all of the questions through, call it 218 at least, and probably 219. If you're not able to get through all those, my hope is that you can come with a repository of questions that you can grill me on when we're back face to face, and I can get you through each of the ones that you're not 100% certain about. But let's just kind of skim through and give you a walkthrough of what type of things that you're looking at. The first couple questions are just kind of warm up questions. Given 1 and 2, show that 3 is an equivalent matrix model. That means look at equation 1, look at equation 2, and show me that equation 3 is a system of equations which contains exactly equation 1 n times in it. It's really just making sure that you know how equation 3 comes from the statements we make about individual infrastructure systems. Okay, question 2.2. Explain how to interpret the last row of table 2. Well, we look at table 2, and there's all these zeros buried in it. I already gave you some hints about what that means. You need to comment on explicitly what you think that means and whether or not you think that's reasonable. Question 2.3 basically is asking for you to give a little bit more interpretation to this dependency index and this influence index. Don't just tell me what it means. Reason through yourself exactly what's happening here and try to give me some indication as to why these things should be called an influence matrix or why it should be called a dependency matrix. Okay, question 2.4 really goes on and says, hey, if I give you equation 3 up here, and I give you an F and I give you an A, how do you find X? Give me an explicit analytical solution. It may involve inverses. You may have already seen this before in the lecture slides. So show me how to solve this. When you solve it, you're going to get a solution, something along the lines of X is equal to SF. I need you to tell me what S is mathematically equal to, like how to compute it or how to actually like give it a meaning. And then I want you to walk me through, just like I did in the EIO LCA example in the video recording. Walk me through what the Sij mean. I want to know, like, if you had to define Sij, what is it? And I'd like to know what the column of S, what the first column of S means, what the second column of S means, what a row of S means, and so on. And you can kind of break down your solutions, in 2.5 and in 2.6. They kind of walk you through. I want to know why we would go ask infrastructure operators to give us data on A rather than data on S, which S is obviously going to be this thing that you solve for. Given the final sort of external input, given the earthquake, I want to know the total amount of damage it does to all the infrastructure. Why wouldn't I just ask people directly for S? Hey, if you're the transportation operator, how much damage to the transportation network will you sustain due to an earthquake? Not just the direct damage, but all the indirect damage. I think it's easier, I know it is easier to get good data on A and calculate S rather than trying to get good data on S directly. And I'm just really hoping that you can maybe give some thoughts as to why that might be true. Just like you can calculate column sums and row sums of A, you can do the same for S. I gave an example in the EIO LCA of what a column sum of S means. Here I'm asking you to explicitly define it. Give me, define an overall dependency index and an overall influence index. These are slightly different than the dependency and influence indices. They have that extra word overall. Maybe give me an equation on what those things look like, potentially considering column or row sums. How do we interpret it? I'm mostly interested in a lot of this stuff is like how to actually do the interpretation, not the actual. The answer should be relatively easy to copy paste in from the EIO model, but understanding what it means is, I think, the more interesting and more subtle part that's worth giving some thought to, really trying to understand the model rather than just get a model that computes answers. Then I'm asking you to do more detailed analysis to really probe at what these models mean. For example, by looking at specific coefficients of A for a subset of sectors, And you could imagine trying to figure out what sectors influence my sector the most, and what sectors I influence the most. Another way of saying that is things like, when somebody else is damaged, who does that impact? And when I am damaged, who do I impact? Those are different questions, but they both mean something pretty interesting as you try to analyze systems and figure out who you depend on and who depends on you. Question 2.1 starts to model change the model. You can make the smart grid, or you can make your power network more intelligent by linking it with other technologies, right? That's good. That allows you to get better performance out of things. Smart grid technologies are things like using real-time data on demands, or using real-time information about when people are in buildings and when they're not, to do things like cool or heat the buildings preemptively so that you can better manage your power supply in real time. You might even incentivize people to shift off load by telling them, I can actually charge you less money for electricity if you do things in the evening off peak as opposed to in the evening on peak. Well, adding that extra technology definitely makes you more efficient in terms of electricity generation, but it now adds new dependencies to your system. If you can't turn off or on your washing machine without having the internet active, or in kind of the extreme jokes that people often make in the technology community, like, we wanted really advanced technologies like flying cars. We ended up with things like washing machines that are internet enabled, or toothbrushes that are internet enabled, or I can't wash my clothes or brush my teeth without the internet working. That's kind of a weird dependency where your toothbrush or your washing machine has a dependency on a functioning internet. And if the internet goes out, you can't do basic stuff anymore. Well, the same is true for these more sophisticated smart grid technologies. You might be adding new infrastructure dependencies in there. If the communications infrastructure fails, you might now have new failures in the power network that you didn't have before. You've added new coupling for the benefit of enhanced performance when things are working well, but you might have also created even further degraded performance when things are going poorly. Nothing better than not to depend on a piece of infrastructure. In the case of some of the satellites, if the power network goes out, the satellites have their own independent power system. Well, if you break those dependencies, or those independencies, and make them dependent instead, that means all of a sudden you now have new vulnerabilities to a system that didn't previously have those. So as you start thinking about incorporating smart grid technologies, that will definitely change A. You need to tell me which coefficients would change, maybe estimate how much they would change by, and then we can start to explore what happens when you do that, like in 2.12. You're going to tell me you're going to change, what these coefficients mean, and then you're going to tell me, after you tell me what coefficients you want to change, you're going to change them by 10%, positive or negative as you specify. And then you're going to calculate the new matrix S and look at how things changed. Look at how S changed, look at how some of these indices changed, and I want you to kind of comment on what is changing, why it's changing, and does it make any sense? You change a few coefficients by as little as 10%. Do you see much, does that have any impact? Does that have more than 10% impact, and on what? That you can kind of tease out in 2.12. Now we actually start using the model directly, so I'll give you a sudden strike of a snowstorm that does damage to certain parts of the infrastructure, and I want to know sort of what is the total impact of the infrastructure. Like, what is the total damage to the infrastructure? Are there any parts of the infrastructure that are degraded even though they do not directly sustain an external damage? Which ones, by how much? Which ones sustain a lot of damage? Which ones don't sustain any damage? That'll be interesting to kind of tease out sort of the indirect effects of this strong snowstorm that might be hard to see if you don't have a model to help you interpret. 2.14 basically is an interpretation question. I'm giving you this matrix A, which comes from a very specific type of outage. It's a 6 to 12 hour outage. You're going to apply it to a snowstorm, and I want to know, basically, is that a valid A or not? Obviously, something that sustains damage for months, a 6 to 12 hour interdependency matrix A is not going to be very helpful for something that's on a much larger time scale. So you might comment about how relevant this matrix A would be for a snowstorm or otherwise. 2.15 is maybe a trickier question depending on how you look at it. Basically, what I'm trying to have you do is simulate the dynamics of the damage through the infrastructure. In the slides I gave you this analogy that you can look at the direct effects and the indirect effects and the indirect effects in the economy. The same is true on the infrastructure. This is the external damage. That external damage causes some total damage, but that total damage through A causes additional total damage. Well, since there's now additional total damage, A operated on that total damage again will tell you how much new additional damage you have to the fact that the old infrastructure was damaged a little bit. Well, this looks a whole lot like a time dynamics system that we hope eventually converges. That basically, as incremental additional damage is propagated through the infrastructure network, eventually, as k goes to infinity, as it's iterated through an infinite number of times, you end up with a final total amount of damage to the infrastructure, where, in other words, the x of time k is exactly x of time k minus 1. The dynamics have stopped evolving in time. They are stationary. What does that look like? And look at how x evolves over time k equals 0, k equal 1, k equal 2, and so on to k equal to infinity, and how that xk compares to the x that you calculate from the equation x equals sf. And I want you to comment on whether or not that's just a coincidence that these things line up or don't line up, or whether there's some fundamental reasons to what you plot and what you see. 2.16 is where you get a chance to play around with some of the Monte Carlo stuff that we've introduced. In particular, I want you to consider what happens if you have uncertainty on some of those values of A. So instead of giving the A values I gave you, I want you to randomly draw some A's that have parameters that are random variables that are uncertain. And I want to understand how that generates uncertainty in the total demand. In other words, does a 10% uncertainty on A produce a 10% uncertainty on X? Why or why not? There's lots of ways to explore that. You could do it analytically, or you could do it numerically. I suggest at least starting off on the numerical side to see what makes sense and why. We can look at uncertainty not just in A, but we can look at uncertainty in F. So if the snowstorm is uncertain, but A is known to you, does that change uncertainty? What does that do to the uncertainty in X, the total demand? And so you can set up some Monte Carlo analysis and explore that. And then I kind of want to understand sort of like the worst and best cases. If you look at the upper and lower bounds of your uncertainty distributions and actually calculate for a fixed A where you're using your worst case values, or a fixed F using your worst case values, worst could be the minimums or the maximums or both. I want to understand what that does to X. Is it the worst or the best case, or does it fall somewhere in between? The final one's a bit tricky. But basically what I'm asking for is, if I tell you the maximum amount of damage I want to sustain in total to some infrastructure systems, can you find me the largest F that I can sustain without having my total damage exceed these thresholds? There are many ways to do this, some that use explicitly optimization theory, which you have not seen yet, and I will introduce. I believe that you can also do this without a single line of optimization if you analyze the matrix S cleverly. And so maybe a question worth thinking a little bit about is sort of what it means to talk about making sure that the total damage doesn't exceed these thresholds, and what it means to have a large initial impact. In fact, F, the impact, is a vector, right? So you have to specify the type of disturbance and what it means for the disturbance to be maximal. In other words, I could look at individually I'm only going to damage one piece of infrastructure, and I want to know the largest infrastructure I can damage. I want to be able to really, really hurt one piece of infrastructure as much as I possibly can, but not exceed these thresholds. Or you could say things like, well, I want to damage not just one infrastructure, but all of them. and what's the largest one I can sustain. So a lot of it's going to, your answer here will depend on what you interpret as the maximum initial impact F that you are trying to find. So I'm expecting, depending on how your team interprets this question, you could have something that's really simple and really analytical, or you might have something that definitely requires optimization. And so there's not specifically a right or wrong answer for this question, or really for many of the other questions above, but it depends on sort of how you define what your interpretation of the question is. And your interpretation may be one that is rich in terms of interpretation or not, and that's actually okay. I may provide some additional suggestions on other ways to look at the problem that might be more or less insightful, but that actually generate different types of problems that might be worth exploring. So that's a pretty good chunk to start with for Tuesday and Thursday in class for your team to start diving in. It would be really good for each of your team members to read through this stuff ahead of time to start thinking through some of the problems, and then really getting a plan of attack on how you want to move through that section. And then remember the sort of second part of the project that requires a bunch of optimization theory, we'll be diving into pretty quickly. And so you'll definitely want to get a good jump start on the first part of this project to leave yourself plenty of time to work on what I would argue is maybe the more challenging and rich decision-making part of the project, which gets into really optimization for electricity generating utilities. So we're going to go ahead and stop there. Again, the goal really is to get a big head start on these first 18 or 19 questions on the project in class next week. And we will have both Charles and Will in the classroom to help your teams kind of get the project set up and really start to interpret some of these pieces. So enjoy the rest of your fall break, and I'll look forward to seeing you when I return. Thanks.